Good afternoon. Today I will present a summary of the paper Approximation Algorithms for Combinatorial Optimization with Predictions by Antoniadis and co-authors. This is an exciting recent paper because it combines two worlds, the world of provable approximation algorithms and the world of predictions, often machine learned, that we can use to speed up or improve solutions. In the next few minutes, I will go over the motivation, the problem model, their main black box technique, a defined algorithm for the Steiner tree problem, their theoretical results, experiments, and practical techniques. Let's begin with why this work is much needed. The main point of this paper was basically the predictions can improve approximation quality without slowing algorithms. The classic combinatorial problem think vertex covers, standard tree, knapsack often have fast approximation algorithms, but the approximation factors can be improved without changing the algorithm significantly. On the other hand, machine learning machine learning can give us predictions based on the instance patterns, for example predicting which vertices are in a minimum vertex cover. The catch is that this prediction may be wrong, sometimes badly wrong. The goal is to design the algorithms that improve quality when predictions are good, and still have the worst guarantee when predictions are bad. The authors target a broad class of problems they call selection problems and show how to integrate predictions in a clean general way. Now for the model and key definitions, here's the main point is the selection problem and how prediction errors are measured. A selection problem means uh, we have some items, each with a weight, and a set of feasible solutions that are subsets of this item. A prediction is any subset of items uh, where x cap belongs to n. We measure prediction quality using two numbers, false positive and false negative. Uh, it may or may not be feasible, but a prediction is any subset of items. The false positive, the total weight of items predicted to be in the solutions but actually aren't in the optimal solution. The false negative are the total weight of items missing from the prediction that actually are in the optimal solution. These two measures allow the analysis to quantify exactly how much prediction can help or hurt. Now coming to the black box construction, the main point of this construction is the set predicted weights to the zero trick. Here's the core trick for the minimization problem. First step, uh, taking my existing approximation algorithm, and then in the second step modify the weights so that the any item in the prediction uh, any item in the prediction has weight 0, keeping the original weights for others, and run A on the W bar and return the solution X. Uh, the intuition of this algorithm is basically if predictions are perfect, the algorithm will naturally include those zero cost items and find on optimal solutions because the rest of the work is trivial. If predictions are imperfect, then I get a bound which is w of x less than w of x prime plus eta plus rho minus 1 into eta minus. So the approximation ratio with respect to optimum is 1 plus uh, eta plus uh, rho minus 1 into eta minus divided by optimum solution. In other words, I only pay for the prediction mistakes, and for the penalty is scaled by the approximation factor for the false negatives. Now coming to the high-level flow of algorithm, this diagram shows the method as a flow. Start with the input and prediction, then modify the weights predicted items to set to 0 to cost, running my existing approximation algorithm on the modified instance, then output the solution. The small box below is an optimal robustification step. You can also run the original algorithm on the unmodified instance in parallel and take the better result. The layout here keeps boxes in one horizontal row so nothing overlaps. That's that's more important for our algorithm. In the next step, the maximization analog examples. The main point of this uh, maximization analog is the same idea that works for maximization problem with a flipped weight modification. For maximization problems, we do the dual, set weights to 0 for items outside the prediction. Then we run the approximation algorithm for the complementary problem. The bound looks like this: that 1 minus rho minus 1 multiplied by eta plus eta minus divided by optimum. The applications include independent set, click, knapsack, and minimum weight matching, often via problem reductions. This is powerful because it's easy to apply to existing algorithm without rewriting them. Now coming to the refined standard tree algorithms, that is ALPS. The intuition behind it, the specializing the approach for standard tree with the ALPS algorithm. For standard tree, they go beyond the simple zero weight trick. ALPS takes the predicted set of edges and scales their weights down by 1 divided by alpha. The confidence parameter here is alpha, which is basically greater than or equal to 1. Then it runs the Milhorn's the MST heuristics on the terminal metric using the scaled weights. The effect of the alpha is shown in the schematic. Small alpha that uh, the small alpha that means robust behaves like an original Milhorn. The large alpha trusts the predictions heavily. The middle alpha balance between the robustness and trust. The refined bound shows that few bad heavy edges that don't explode the cost because they are kept by the minimum spanning tree connections cost. Now here for the theoretical guarantees and lower bounds, the bounds are basically tight for the selection problem class. The black box bound says that the omega, the W of x is less than or equal to the optimum plus eta plus rho minus 1 multiplied by eta minus. The authors prove that under the unique game conjecture, there is dependence of false positives and false negative is optimal for selection problems. You can't do better asymptotically without stronger assumptions. For LPS, they refine the bound to limit the harm from false positive to something proportional to MST connection costs. So heavy errors don't dominate. Now coming for the experimental setups, the ALPS performs well on the real standard tree benchmark. They test ALPS on 199 hard base 2018 standard tree instances. The baseline are Milhorn's heuristics, which is the first part 2 approx and CIMAT, which is slower but near optimal. With accurate predictions, the ALPS with alpha around 1.422 achieves near optimal quantity with the same runtime as Milhorn. With bad predictions, ALPS is almost as good as Milhorn, so it's robust. Plots in the paper show approximation quality versus prediction noise parameter P, so it's robust. The smooth degradation as P increases. Now coming for the practical recommendation, how to apply this in practice. If you have first row approx and the predictions, then it's possibly infeasible. Predictions from any source, heuristic, ML, or human guess. Applying the black box method for standard tree tune alpha to 1.422, run a small set of alpha values, then pick the best. Consider running the unmodified algorithms in parallel for safety. Cost is just a constant factor. Then coming to the conclusion, this work gives a simple problem independent way to improve approximation quality using predictions which is with provable smooth degradation. It's optimal for selection problems, and problem specific refinements like LPS can do even better. The future work extends to the problem that aren't selection problems like clustering or scheduling, and designing better learning methods tuned for these algorithms.